Hey everyone, we are at Unit 11. That's the good news. We are at the second last unit of the course. And the topic that we're going to look at this week is another violation of the classical assumptions. This time we're going to look at what happens when the x variables are random. So we've been assuming that they're non-random, and we've used that assumption all throughout the course. It's very important. The bad news is if those x variables are random, then a lot of results from OLS become unreliable. So the slope coefficients become biased and the variances become biased. So we need to figure out how to test for it and what we can do to try to fix it. The topic of this unit is called endogeneity for reasons that I will explain. We could call it randomness of the x's, but again, for reasons I'll explain, in econometrics we call it endogeneity because the reason the x variables are likely random is that they're endogenous variables. What am I talking about? Well, just hold on a few minutes and you'll find out. So grab your pens and your paper and we will get started. Now, before we begin, let me just say that at this point in the course, I would normally be looking out at a classroom of very stressed kids, and I would see it in your faces that it's been a long semester. You've been working hard. You've got this course, you got other courses, and you're heading into the home stretch. You're thinking about exams, you got final assignments, and I can just tell that everyone's getting to the limit of what they can survive in a semester. And doing this all by video means I don't actually get to see you face to face. And this isn't actually the end of the semester when I'm recording this video. But I am aware that at this point in the course, you guys are just trying to stay afloat, just trying to stay on top of the material. And I'm going to do as much as I can from now till the end of the course to just keep it as simple as possible, give you the material that you need to complete the course and get you ready for your final exam. And I wish that I could see you face to face. That's the other thing. I miss the interaction with the students, and I get a bit of interaction electronically, but it's not quite the same. So let me just try to convince you, though, that I am aware. We've covered a lot of material in this course, and I know most of you are taking other courses, and you are doing a great job of staying afloat in the material, and we're going to get through to the end. And so stick with me for a couple more lectures because we're almost there. So this one is the material from section 5.5 in the textbook, and it has to do with random x's. Okay, so we've been assuming up to this point that the x's are fixed and not random. That is classical assumption 5. Classical assumption 5, the x's are fixed and non-random. And it's a bit odd. We kind of skated past the terminology there. And generally what that means is that when we take expectations involving the x's, we can just take it outside the expectation without worrying about any correlations that might be present between the x's and the actual random variables. We'll try to make it a bit clearer today what this assumption really means. I do need to introduce a bit of terminology. I think I've used this word before, but the word is endogenous. And to define it, I'll start by its opposite, exogenous. Exogenous means the value is determined outside the model. Endogenous means the value is determined inside the model. Inside the model. So, okay, so what does that mean? Well, let's say that we have a regression equation, and we're going to do a regression model to investigate whether policing reduces crime. All right, so our regression model is, so we've got observations on crime rates in neighborhoods all across the country, and we have data on the number of police officers stationed. And so we're going to run a regression that'll look like this. So we've got crime rate and we've got the number of police. And our expectation is there should be an inverse relationship. That the more police there are in a city district, the crime rate should go down. However, we have an endogeneity problem here, which is that would be true, that normally you would hope that the more police you put in an area, the lower the crime rate goes. But at the same time, police are assigned to areas based on the crime that's there. So we will also have a positive relationship between these two variables, because if crime rate goes up in a certain neighborhood, then the mayor will send more police to patrol that area. So policing is a function of the existing rate of crime, as well as crime being a function of the amount of police that's there. So the causality can go both ways here. So both crime and police are endogenous variables. They're both determined inside the model. Let's think of another example, though. Let's have crime equals alpha plus beta times, let's say we've got data on the historical average income. All right, so that'll be like the average income in a city over the past 30 years leading up to today. Well, this is exogenous. Okay, so the average income over the past 30 years is not going to be determined by the future crime rate. So this one would be exogenous. It's determined by something outside the model. So this variable is exogenous, and this one is endogenous. So our model says, let's suppose the crime rate is determined by the income level, whereas in this case, that's endogenous, and this one's endogenous. So endogeneity of the x variable, as we will see, that causes it to be a random variable. And so that's one of the things that can cause this assumption to be violated if we have endogeneity. Now, there can be other things that cause x to be a random variable, as we'll see, like measurement error would be another one. But we typically encounter this as a problem when we have an economic model with endogenous variables on both sides of the equation. And it can happen, it can be very common. If you think in macroeconomics, for instance, if you have GDP is a function of consumption. Okay, if you ran a regression like that, well, then you've got this problem that consumption is determined, among other things, by income, which is driven by GDP. So consumption depends on GDP, and then GDP also depends on consumption. So we need a way of dealing with that. Okay, another note that I want to put here is one of the results that we learned earlier in the course is that the expected value of A and B are two random variables, and the expected value of A times B equals the expected value of A times the expected value of B plus the covariance of A times B. I believe that we learned that earlier in the course. Let me just check. Looks like we didn't. But anyway, now we've learned it. So the expected value of A times B, if these are two random variables, is expected value of A times the expected value of B plus the covariance of A and B. That means that the expected value of A times B will equal expected value of A times the expected value of B. That will be true only if the covariance is 0. Okay, so you can see that obviously there. If that covariance equals 0, then we're only left with that smaller portion of the equation. All right, so you got that. One other thing I want to review is consistency. Now, I gave you a kind of a muddled introduction to consistency when we were talking about the heteroskedasticity consistent estimator. And it is in the textbook. But let's go through it one more time. Okay, so consistency. We talk about estimators being consistent. And so it's like unbiased, but it's based on the sample size. When something is consistent, an estimator is consistent, that means that it's going to collapse on the true value as the sample size gets very large. So I'll give you an example. Let's start with x, and we'll say it's a normal random variable with a mean mu and a variance of sigma squared, and we have a sample size I equals 1 to n. And then we have x bar, the mean of x, and that, of course, is 1 over n times the sum of xi. X bar, this is a consistent estimator of the mean of the x's. And to prove that, we just need to calculate the expected value and the variance. So the expected value of x bar is 1 over n times the sum of the expected value of x bar, or sorry, of xi. And so you see that I've just taken the expectation inside the summation, which we're allowed to do. That's 1 over n times, now this is the sum of n values of mu. So each of these, the expected value of x is mu every time. So we add up n of those and we get n values of mu, and then the n's cancel out and we have mu. So the expected value of the mean of the x's is mu. The variance of x bar is, so if we take the variance, I'll just write it out, variance 1 over n times the sum of xi. So we can take the 1 over n outside because it's a constant, but we just have to square it. So it's 1 over n squared. That's n squared down there. Times the sum of the variance of x. And so each of these is the same. So the variance of xi is sigma squared each time. So that's going to be 1 over n squared and we have n values of sigma squared. And so then one of the n's cancels out, and we're left with sigma squared over n. So that means we can write that x bar is distributed normally with a mean of mu and a variance sigma squared over n. So in this case, the distribution of x bar depends on the sample size. If we draw what the distribution looks like for one value of n, and then we change the sample size, the distribution will change. But that's not true for x itself. So this distribution, you can see because n isn't here in the parameters, this distribution doesn't depend on the sample size, but this distribution does. So as n goes to infinity, this is what we're going to write. X converges in distribution to n mu 0. So this terminology here, that an arrow with a d on top, it says converges in distribution. In other words, its distribution converges to this. And the important thing here is the variance is 0. So what we have is, so the distribution of x bar initially it's like this with, let's say that's n equals 50 observations. And then we go up to 1,000 observations, and the variance is getting smaller. I'm going to end up making a mess of things here. That then equals 1,000. And as n gets larger and larger and larger, what happens is the distribution just collapses onto a single point. It just becomes this giant spike. All right, so as n is getting larger and larger and larger, and then as n goes to infinity, it converges to a distribution that consists of mu and 0 variance. So in effect, it's just a straight line. And the terminology for that is, we say, since it's a limit, we're talking about a limit here, we call it a probability limit. Or plim for short. So the plim of x bar equals mu. So in the limit, x bar collapses onto mu. The probability limit of x bar is mu. In the case of x, by contrast, up there, since n doesn't enter into it, we would say that xi converges in distribution to the normal distribution mu sigma squared. In other words, it converges in distribution to where it started, which is with that distribution. But x bar converges in distribution to a distribution with 0 variance. And so now back to consistency. Consistency is an estimator whose plim is the true value. All right, so you remember when we talked about an unbiased estimator. An unbiased estimator is one where the expectation is the true value. So the expected value of beta hat equals beta. So unbiased means the expected value of beta hat equals beta. Consistent means the plim of beta hat equals beta. And that's a little bit different because in a small sample it could be the case that beta hat might be a biased estimator. If we're working with a type of model or an estimation rule where sometimes in a small sample it's a biased estimator, but the bias goes to 0 as n goes to infinity. And so if you have consistency, that's a pretty good result. Sometimes we work with estimators that are biased but consistent, meaning if you only have a small sample, you don't have a very reliable estimator, you might have a biased coefficient. However, if you can get enough data, then that bias problem goes away. All right, so consistent, you can think of it as being like, well, it's asymptotically unbiased, but also asymptotically the variance of the estimator shrinks to 0. So let's go back to our regression model. And we're using our simple one variable regression. And now we're going to assume that the x's are random. And we have an expectation that the expected value of x is mu of x. And the variance of x is sigma squared x. And if we use OLS, then as you know, we get the formula for beta hat is the sum of x, y over the sum of x squared. And from the standard decomposition of this result that we've used before, that is beta plus the sum of x epsilon over the sum of x squared. And then previously, when we take the expectation of this, we've always been able to invoke the fact that x is non-random, so it's a constant, and we can bring it outside of the expectation. This is the step now where we can't do that anymore. We're going to run into a problem. So if we take the expected value of beta hat, that will be beta plus the expected value of, and I'll just rearrange this a little bit, so it'll be the sum of x over x squared. Oops, sorry, this is the summation under here, times epsilon. So this expression here is equivalent to that expression there. Now, let's look at a simple case first of all. Suppose that the covariance of x and epsilon is 0. So x is random, but it's uncorrelated with the error term in the model. If that's the case, then this expectation will be, well, let's have a look, sum of x over the sum of x squared epsilon. All right, let me think. So these are uncorrelated, so I can use that formula that I had earlier. I'll take the summation, or I'll take the expectation inside the summation here. So it's going to be x over the sum of x squared times the expected value of epsilon. So because the covariance is 0, I have essentially the expected value of A times the expected value of, or the expected value of A times B. And that is equal to the expected value of A times the expected value of B. because the covariance is 0. So I've got the expected value of the error term on its own. That goes to 0, so the whole thing goes to 0. So that means beta hat is unbiased. And we won't go through the variance calculation. The formula is the same. In this case, the randomness of the x's means that in small samples this could be biased. So the variance estimator here is consistent. So we can say it's consistent. So we have an unbiased value of beta hat, and a consistent variance estimator, which in other words means go ahead and use OLS in that case. It's like the heteroscedasticity case where we use White's correction, and then we have an unbiased slope coefficient and a consistent estimator of the variance. Okay. The second case is, suppose that the x's and the error terms are correlated. They have either positive or negative covariance. And this is important because this is the case, this is what endogeneity gives you, that it causes the x's and the error terms to be correlated with each other. All right, so then it just means we can't make that reduction. We get the expected value of beta equals beta plus the expected value of the sum of x times epsilon divided by the sum of x squared, and we can't decompose them like that. So we actually can't go any further than this. What we have is this term here that we can't reduce. So that means OLS is biased and inconsistent, which is bad. Unlike the autocorrelation and heteroscedasticity case, where we have a problem with violating a classical assumption, but we still at least get unbiased coefficients. We just need to try to fix the variance estimator. Here, we get biased coefficients. And I can tell you from experience, having worked with these kinds of models where you're working with economic covariates where you've got endogeneity, and these slope coefficients are just, they go crazy. You can get all kinds of weird numbers. And like you can sort of see what would happen if you think of the crime and the police example. If you collected a whole bunch of data on crime rates and police, and you just plot them as a scatter plot, it's not going to be some nice, neat, downward sloping line, because, as I said, that's part of what's going on, but you also have the positive correlation driving this. Or if you take market data, for instance, if you want to estimate demand elasticities for for coffee. Let's say you work for a big coffee company and you want to study your market, you're going to estimate demand elasticities. Well, price and quantity, there's a demand curve. There's also a supply curve. So as the price goes up, more suppliers appear. And so price is a function of quantity, but quantity is also a function of price. So that was one of the first examples that economists tried to grapple with when they were doing econometrics, and got computers that can calculate all these wonderful things for you, but how do you calculate a demand curve when you've got endogeneity? What's the solution? The solution is a technique called instrumental variables. Instrumental variable estimation. instrumental variable estimation. What it means is we have to go outside the sample and get some information outside the sample that's going to provide an anchor for our x variable. So we're going to look for a variable z where we have reason to believe that it meets two conditions. Z and x are correlated, but z is independent of the error term. And since this is unobserved and it's kind of hard to figure out what's really driving the error term, it's usually more the case that we think of that z is independent of y. So z will be a number that's clearly not determined by the y variable. So in the case of a demand curve, let's say you're going to estimate your demand curve. So the quantity is a function of A minus B times price. So we would want an exogenous variable that is correlated with the price, but that is uncorrelated with the market demand. So let's see, what would drive the price? Well, it's the marginal cost of production. And let's say this is a commodity that's made somewhere else and it's imported. So you might have data on, say, labor costs in the country of origin, and those labor costs aren't driven by the quantity of coffee that's consumed in the province of Ontario. So that would be a candidate as an external anchor on your price. So that would give you some indicator of something that drives changes in price, but isn't driven by Q in this case. So it's correlated with price, but it's independent of the error term and alternatively the dependent variable. Let's think of crime equals A minus B times police plus an error term. So in this case, what we'd want is an instrumental variable that has some bearing on the amount of policing that's done, but that isn't in response to local crime rates. And that can be kind of tricky to identify, but let's say that there was a program, let's say unexpectedly a new immigration program was introduced which encouraged immigrants to move to a certain city. They sometimes do this. They don't want everybody crowding into one city, so sometimes there'll be a resettlement program for new immigrants that says, well, we'd really like you all to move to Kapuskasing or someplace like that. So you get a whole bunch of immigrants, and as part of the program, they also say to the city, and we'll boost your budget for policing and fire services. And so it's an unexpected change in the budget for police. Those are sometimes called natural experiments in economics literature, where you have some outside event that induces a change in this variable, and then that means that you've now got some strictly exogenous change in the explanatory variable. And then if you look at the data before and after that program, that'll give you some information about how crime changed in response to policing, without the change in policing being dependent on the amount of crime. there isn't a formula here. So this is where it takes modeling expertise and economic analysis, and you have to, when we do studies that involve instrumental variables, you have to explain to the reader, well, this is what the instrumental variable is, this is why I think it would work. And but as we'll see, there are tests that you can apply to see whether your instrumental variable is any good, and then also whether it helped resolve the endogeneity. But let me show you why this works. So let's suppose that these conditions hold. So let's go back to our regression model. And we're going to multiply both sides of the equation by z. So we'll have yi zi equals beta x z plus z epsilon. Okay, so we've just multiplied through by z. Multiply through by z. And now we're going to add everything up on both sides. So add up across the sample. And I'm going to add that up, but I can bring beta outside the summation. And now I'm going to divide both sides of this equation by the sum of x times z. So I'll have sum of yi zi divided by the sum of x z equals beta plus the sum of z epsilon divided by the sum of x z. And now if I take the expected value of both sides, the expected value of that term there will be, well, I've got the expected value of a constant, so I get my constant back, plus, and then I've got the expected value of this thing. Sorry, summation. And because I've chosen z so that it's independent, or it's uncorrelated with the error term, then for the reason that we saw last time of taking the expected value of a times b, I'm going to have the expected value of epsilon on its own in there, and so this will go to 0, and I'm left with beta. So that means this would be a good estimator. All right, so let's use that. And I'll call that my instrumental variables estimator. It will be the sum of z y divided by the sum of x z. And so it's unbiased. All right, so I've solved that problem, that it's an unbiased estimator for the reason that I just showed you. Now let's see what our distribution looks like. So the expected value of z, we'll call that mu of z, and the variance of z is sigma squared z, and we've assumed that the covariance of z and epsilon equals 0, and we've assumed that the covariance of z and x is not 0. That's why this is a good instrument. These are our instrumental variable conditions. That it's uncorrelated with the error term, but it is correlated with the x term. Then what we can show, you can probably do this in your head, actually, but I'm just going to write it down, that the variance of beta will be sigma squared z plus mu squared z times sigma squared, which is the variance of the original error term, divided by n, which is the sample size, sigma x z plus mu x mu z squared. I was just kidding when I said you could probably do that in your head. If you could do that in your head, you don't need to be in this course. And we will just give you your PhD now. We're not going to derive it, and I don't need you to even know it. But you can look it up if you want to see how that comes about. The important thing I want you to see, though, is look at what's down here in the denominator. N is in the denominator. So that means that as the sample size gets larger and larger, this is going to go to 0. So that means that the probability limit of beta hat IV equals beta. So it's a consistent estimator. And that the reason is that as n goes to infinity, the variance of beta hat goes to 0. So it would still be consistent even if, like if we go back here, even if there was a bias term in here, if this was a little bit biased, but the bias was something inversely related to n, so it goes to 0 as the sample size gets large. However, that's not an issue. There's no bias, so it's unbiased regardless of sample size, and the variance goes to 0 as the sample gets very large, and so it is consistent. I should have shut the ringer off on my phone there. My daughter is texting me about something. So that's the basics of the technique. We're going to the solution here is you want to find an instrumental variable that has these properties, that you have reason to believe it's uncorrelated with the error term, but it is correlated with the x variable. Now, you're not limited to just one z variable, though. You could use multiple z's. And if you do that, that's called a generalized instrumental variable estimator. So if you're going to use multiple z's, then you would just form a regression model. So you're going to regress x on, say, gamma 0 plus gamma 1, z1 plus gamma 2, z2 plus a new error term, so I'll call it u. That's the error term here. Okay, so let's use a couple of z's, and then you obtain the fitted values. And that's your instrument. And so then it becomes clear why your instrument has to be correlated with x, because if z and x are uncorrelated, then these will give you lousy fitted values. It won't track the movements in x at all. And so if they're good instruments, then they have to be highly correlated with x. They have to explain the variance in x. But otherwise, it's just the same as before. Now we call it the generalized instrumental variables estimator, or give. Beta hat give equals the sum of x hat yi over the sum of x hat. And again, this is consistent. It is a consistent estimator. So that is that's how we deal with the random x problem. the random X problem often arises from endogeneity. It can arise from other problems as well. Random X's can arise from, so I've talked about endogeneity. Another one is measurement error. Let me just see. So let's say y is xi beta plus epsilon. That's the true model, but we don't observe the true value of x. We observe x star equals x plus some noise term or some random term v. So then this model becomes y equals, so we have x star minus v beta plus epsilon. So without realizing it, that's what we're actually running, because we're using x star. And there are lots of times when we don't observe exactly what we want to observe. We observe it either with measurement error or some other limit to what we can actually observe. For example, in macroeconomics, consumption decisions. Some of your consumption decision is based on your actual income, but it's also based on your expectation of what we call your permanent income, or if you anticipate over the next 10 years you're going to be earning a certain amount, then that's going to influence your consumption decisions, because you'll be willing to borrow money. For instance, you might take on a mortgage, you might take out a loan, expecting to be able to pay it back. So what really drives consumption decisions isn't just your current income, but it's your expected permanent income. And we don't observe the expected permanent income, but that's really what's driving the consumption decision. What we observe is the actual income, which is an imperfect estimator of permanent income. So if we have that model, then we have beta x star plus a new error term, which I'll call epsilon star. And if we factor everything out there, then epsilon star is epsilon minus beta vi. And then if you take the correlation, if you compute the covariance between x and epsilon, between x star and epsilon star, then that is, it works out to be minus beta times sigma squared v, where sigma squared v is the variance of this error term. And I'm not going to go through the steps. It's just a matter of taking the expected value of this times this. But the main point is that that's not zero. So here we have, the problem is we don't observe the variable that we want to observe. And so we end up with a non-zero covariance, and then you've got all the problems from before, that the calculation of bias we can no longer do the way we want to do. So in terms of economics, both of these can come up. The endogeneity problem is particularly difficult. You have to be very careful about it. It comes up in lots of models. It comes up in labor market models, for instance. The determinants of wages, wage and education, for instance. We would expect if you regress wages on the amount of education, well, they go up with each other, because the more educated workers earn higher wages on average. But the education that a person gets may also be determined by the wage that they expect to earn because they have an innate ability. So it could be that both wage and education are jointly determined by innate ability. And so that can cause an endogeneity issue. And there the issue is both the y variable and the x variable are jointly driven by some other variable that's outside the model. And so they're both endogenous, and then you can get an endogeneity bias. So in the assignment, the third assignment, when you worked with another data set that had the schooling of the father and schooling of the mother, that kind of data set is built for labor market studies where you can use the schooling of the father and the schooling of the mother as strictly exogenous variables to serve as instruments for the explanatory variables. Because the schooling of the father is not going to be determined by the innate ability of future children. Same with schooling of the mother. I mean, they're basically determined before the children even appear. Except for, in my case, actually, we had our daughter while we were in grad school, so they overlapped a bit. But I think it's still going to be the case that the schooling of the father is not strictly determined by the innate ability of the children. So I think that's where I'm going to stop. I want to talk next time about the testing. So how do you test if you have an endogeneity bias problem? We'll have a couple of tests to talk about. One is, do you have an endogeneity bias, or the test for whether you need to use an instrumental variable, and then the test for whether you've got good instruments or not. That'll take us to the end of this material. And I'm going to, in the next lecture, I'm also going to talk you through the first question in this unit, in the lab for this unit, because it's a hard question. I should have put it at the end of the list, because if you start with that one, it's kind of hard, and then that might make you think you don't want to bother with the rest of them. But it's actually the hardest one. So, and the solution's there. Your TA will go through it, but it's a nice demonstration of how endogeneity bias arises. So we'll talk about it next time, as well as the testing, and then we'll be done. So I will talk to you next time.